A rational function is one that has x in the denominator. It is a fractional function. It's a ratio of two things. And the important thing that makes this a rational function different from a linear function is x shows up in the denominator. For this particular function, there's what we call a horizontal asymptote at y equals 0, because as x gets really, really huge, as we plug in bigger and bigger numbers for x, y becomes essentially 0. It gets smaller and smaller and smaller. We could say that the limit, this is an important thing, I'm introducing it here, as x approaches infinity of 1 over x is 0. Likewise, the limit as x approaches negative infinity of 1 over x equals 0, but this time it's going to approach from the bottom. Well, we also happen to know that for anything with x in the denominator, what can't x be? Well, x can't be 0, so we have this vertical asymptote also, which has an equation x equals 0. Now, there's a couple nice points that we could plug in. When x is 1, we're here, and we're here. And otherwise, it just gets real close to these two asymptotes as we go. This is what a rational function graph looks like. This is what we call a hyperbola. Hyperbola. Now, let's get more complicated over here. We could make a big table of values. We could use our calculator, but you know what? We're too good for that. We don't need it. We're okay. Think about the denominator. As x, well, what can't x be? Well, x can't be 1. So that means that we have a vertical asymptote there. And on the graph, we always label it with the equation x equals 1. That's the graph that's the equation that our graph is going to get closer and closer to, like here. Now, what about a horizontal asymptote? To figure that out, ladies and gentlemen, we're going to use something called this limit, and we're going to look at what happens as x approaches infinity. Now, as x gets really, really huge, the numerator also gets really, really huge. As x gets really, really huge, that is, x goes to infinity, the denominator gets really, really huge. So we have something really huge divided by something really huge, and that doesn't really help us out very much. So we have to make a small algebraic manipulation to evaluate this limit. And what we're going to do is we're going to divide each term by x. 2x over x is 2, plus 3 over x over 1 minus 1 over x. Now, let's think about what happens as x gets really, really huge, as x approaches infinity. The numerator, as x approaches infinity, the 2 stays 2. It doesn't care what x is. It's like the honey badger. 2 don't care. But as x approaches infinity, 3 over x gets closer and closer and closer to 0. As x approaches infinity, the 1 on the bottom, the 1 don't care. 1 don't care what x is doing. 1's another honey badger. We've got 1 minus 0. So this limit is equal to 2, and that becomes the equation of our horizontal asymptote, y equals 2. We show that on the graph as such. Okay, so now let's think about other important features of this graph. Well, an important feature would be the y-intercept. Y-intercept is when x equals 0, so plug in x equals 0. We've got 2 times 0 plus 3 over 0 minus 1, so the y-intercept is negative 3. Right there. How about the x-intercept? X-intercept is always good. X-intercept is when y equals 0, and since this is a fraction, the only way that fraction can become 0 is if the numerator equals 0. So when does 2x plus 3 equal 0, guys? Well, that happens at x equals negative 3 halves, negative 1 1/2. So right there, we have enough that we can roughly sketch in this curve, it should be coming from our asymptote over here and approaching our asymptote there, going through the other 2 points. And then somewhere up here, if you want to get more precise, you could plug in other x values, but there's going to be another branch opposite it that roughly mirrors what this branch looks like. And there we go. There's our sketch of y equals 2x plus 3 over x minus 1. But before we leave, what's the domain? The domain is all real numbers except x cannot be 1. And the range, this goes up and down forever and ever, except y cannot be 2. Hopefully you corrected that on your own paper. And there's our domain and range. And the last special type of graph that we're going to look like is something called a piecewise function, and it looks like what's right here. You last saw this when I was talking about the absolute value graph, and we're going to go into it in a little bit more detail here, but it's called piecewise because it comes in 2 pieces, or maybe 3 or 4 or 12 pieces. But there's more than one piece, and we look at each one of them separately. So let's start with x plus 2. I'm going to just graph y equals x plus 2. That has a y-intercept of 2 and a slope of 1. So there we go. But this says that I only use x plus 2 when x is less than 2. Well, where's x equals 2 on this? It's right here. But it's less than 2, not equal to, so I'm going to put an open dot there. And less than 2 would be all of the points on this graph this direction. These other points up here, I don't care about anymore because those come from x values greater than or equal to 2. Okay, so that's that part. Now let's look at x squared minus 3. Well, this is a quadratic that shifted down 3 units. It has a vertex right there, and we could plug in x values and get a graph that looks like this. It has a line of symmetry through the origin. So that would be the entire graph of x squared minus 3, but I only want it when x is greater than or equal to 2. Well, where's x equals 2? That's this point, and since it's or equal to, I'm going to put a solid dot there, and then I'm going to connect going greater than that this way. And all the rest of these points I really don't care about. And I just got rid of my axes and a bunch of other stuff too. But these other points I do not care about. I would leave them off. I would erase them if I wasn't concerned that I'd lose my whole graph like that. So this has 2 distinct parts. Sometimes these 2 points will line up with each other. Sometimes they won't. This is what we call a jump discontinuity. Jump discontinuity. What's our domain? Well, we go forever to the left and forever to the right, and every point is accounted for, even x equals 2, just happens to switch y values. Our domain is all real numbers. Our range, do we go up forever? Yes. Do we go down forever? You bet. There's a jump here, though. Well, that's okay that there's a jump. The range is y is an element of the real numbers because this jump is covered by this part of the graph here and that part of the graph there. Every y value is essentially covered up in this graph. So with these piecewise functions, you graph one piece, then you graph the other. It can be a little bit confusing just because it looks weird and different and we're not used to graphing things that have discontinuities in them, but that's okay. Just roll with it, give it a try. And that, ladies and gentlemen, is where I leave you for today. These graphs are wicked fun. You should be able to identify the basic shape of any of the previous functions I talked about. Piecewise graphs, though, don't have a general shape. It depends on the 2 pieces that we have.